In this video, I will illustrate how to solve a thermoelectric problem, nonlinear problem, in the frequency domain. So we have a tiny aluminum wire with 1 amp AC flowing in. This heats up the wire. It heats it up in a way that has a constant temperature, and the temperature swing around that is at double the electric current driving frequency, because the Joule heating is the current density times the electric field, so it's nonlinear. And so when you drive with, let's say, 5 hertz, 1 amp electrically, you will have a temperature that is a DC component plus an oscillation at 10 hertz around that DC component. In this software, you don't have to do a transient analysis for that. You don't have to do a small signal analysis for that. You can simply brutally in one go get the full nonlinear frequency solution thanks to the harmonic balance method that is natively available. Now let's go immediately in the demonstration. So, thermoelectric AC. So let's focus on the essentials. So I'll just draw a very simple geometry. I will take a piece of aluminum that is small enough so that it has the time to actually cool down at what I mentioned was 5 hertz, sorry. So that we can really see the temperature swing around the DC value. We assign our materials. Here, aluminum. And then we add our physics. These will be current flow and thermal conduction in solid. They apply on the whole region, so we don't have to select the volume. And we can set up our current flow simulation. So we could set an electric ground on the right side, for example, 0 volts. And on the left side, we could let a current flow. So we could say that we have 1 amp flowing. Now we have a 1 amp AC current flowing. This is why we multiply by SN1. SN1 means sine 2 pi ft, where F is my driving frequency. Here, I will choose it being equal to 5 hertz. And then I select my surface here. So 1 amp flowing AC at 5 hertz. We'll define the 5 hertz later on. But at the fundamental frequency 5 hertz, I have 1 amp real part of the driving. This is it. Now I can set up also the thermal problem. I could say that I have a thermal ground on the left and the right end of this little beam. And this is just a reference temperature, so I could choose that this is 0 and meets 0 Celsius. Last thing to do, the Joule heating coupling. This applies everywhere. This Joule heating is the nonlinear part of this problem. We are ready to move on to the simulation. I could already mesh the geometry. Nothing complicated going on in terms of solution profile. So the electric potential, linear increase in temperature increasing as we go to the center of the beam. So this mesh is definitely fine enough to capture what's going on. Next step, I could set the analysis type. So here, harmonic means frequency analysis for linear problems. You might be tempted to do a transient analysis here, but it's not needed. You can go for the harmonic balance method, which is natively available here and called multi-harmonic. So there we go. Fundamental frequency. This is the driving frequency of my 1 amp current. So next step, the harmonics. I will choose harmonics 1, 2, 3, 4, 5. What does that mean? It means that all the fields, unknown fields in the simulation, so here the electric potential and the temperature field, will be approximated by a finite sum of Fourier coefficients. So 1 is sine, it's cosine at 0 times 2 pi ft, so it's cosine of 0, so this is 1. So the 1 encodes the constant part of the solution. 2 is sine at 2 pi ft, it's the real part at the fundamental frequency drive here 5 Hertz. 3 is the cosine of 2 pi ft, so cosine at the fundamental frequency 5 Hertz. 4, it's the sine at 2 times 2 pi ft, so it's the real part at double the fundamental frequency, also at 10 Hertz here. 5 is the same, but for the cosine. If I would add 6, it would be the sine at 3 times 2 pi ft, so it would be the real part at the third harmonic, so at 15 Hertz. And you can cherry pick any frequency you want, any harmonic, so you can have even problems with absolutely different time scales and still solve them with ease in the frequency domain. Now, in this case, we have a sine 2 pi ft drive of 1 amp. So electrically, we will have here only the harmonic 2. But thermally, we will have, due to the Joule heating, we will have the harmonic 2, so J times E, so sine square. We'll have a sine square. Sine square, it's a constant component, so that is harmonic 1, plus a cosine at double the driving frequency, which is harmonic 5. Then we'll also have thermally the harmonic 4, because we have some thermal time derivative in the thermal diffusion. But what we will not have in the thermal solution is harmonic 2 and 3, simply because they are not excited by the Joule heating when you drive the electric part with harmonic 2. So these 5 harmonics will allow us to solve exactly the time response of this problem without actually even any Fourier truncation approximation, because this is representing exactly the time response. Now, next step, I define my outputs. What do I want to see? Well, for example, the electric potential. Got to press apply the electric potential, I said. Now, we don't have to check them all. We know that they will only be the harmonic 2 drive, but the thermal part is more interesting, so let's also add the temperature solution. And let's keep all harmonics 1, 2, 3, 4, 5, and we should see in the end that you have harmonic 1 that is non-zero, 2, 3 that are 0, and 4 and 5 that are also not 0. Now, we can simply run the simulation. And in terms of computing power needed, of course, here for the temperature field, you will need 5 times the unknowns of if you had only a, let's say, steady state static analysis. So computationally, this is more heavy, but the cloud is available to you. So the computing power is still largely enough for very large, tens of millions unknown problems on really complex geometries, even for nonlinear frequency harmonic problems. But you will get a crystal clear frequency response of your solution. You will not have to do transient analysis, so this will make things easier to set up, and you will get very likely the solution faster than with a transient analysis, especially for situations where you have like vibration with low losses, where reaching the steady state takes forever in the transient analysis. Now we can inspect the visualization, and we could check first the electric potential field. No surprise here, linear decrease, 0 volt on the right, and 2.5 millivolts, which is such that you actually have 1 amp flowing. So this is one Fourier term for the electric potential, and you have to multiply it in time by sine 2 pi ft, where f is 5 Hertz. This is for the electric potential. Now for the thermal part, we have T harmonic 1. So it heats it heats in the center, and then we have the 0 Celsius thermal ground on the side. So as you go to the center, it becomes more hot. We have 70 milli Celsius heating going on at the DC. So the temperature will be this 70 milli Celsius, flat constant plus some oscillation. And what is this oscillation? A way we can investigate. We say that there would be no oscillation at the fundamental frequency of 5 Hertz. And this is indeed the case. So nothing going on there, exactly nothing. Same for harmonic 3, exactly nothing. And then something will appear at harmonic 4 and 5 due to the nonlinearity. Now, this is the sine 2 times 2 pi ft. So at 10 Hertz, the real part of the vibration, of the oscillation of the temperature around the DC part. And then we can also check the harmonic 5, which will be bigger, and it is actually here quite close to the harmonic 1, which is unsurprising because you have sine square is something like 1/2 on the DC side and 1/2 of the cosine at double the driving frequency electrically. So you should have, if you have no big heat capacitance effect going on, you should have the same amplitude for the harmonic 5 as for the harmonic 1, but with a minus sign. This is it for this video. If we have, and we hope to see you in another video. Thank you for watching.